This last section of 7 is classifying chemical reactions. Things can be put into different categories. When you were in preschool, you may have been given a bunch of objects to sort. And you can sort them by color. You put all the red ones together and all the blue ones together. You can sort them by shape, putting the square ones and the round ones. You could sort them by size or by what they're made out of. And so one object could be red and round and made out of wood and be small. Okay? So chemical reactions can belong to more than one type. And there are different ways to classify, just like we can classify by color or by shape. We can classify by what happens or by what the atoms are doing. So let's first look at classifying by what happens. So these are the categories. A precipitation reaction. You mix two solutions together and a precipitate forms. It's by observation of what happens. Okay, so that's a precipitation reaction. We have acid-base reactions where an acid and a base react and are neutralized. Gas evolution reactions give off gases. Oxidation-reduction reactions are a little harder to observe directly. Combustion reactions are pretty easy to observe, something burning. So these are the categories for one method of classifying reactions. The other way to classify them So the other way to classify chemical reactions is by what the atoms do. And so here, it's easier to actually look at the balanced chemical equation and see what's happening rather than looking at the actual reaction. So these categories are synthesis or combination, decomposition, displacement, often called single displacement, and double displacement. And these are the general patterns for those. The previous classifications, these guys, we have already gone over those. We've discussed those different types of reactions. So now we're going to talk about this other way of classifying. In a synthesis reaction or a combination, you have two things combining to make one thing. And that's how you recognize it. The example here, sodium metal and chlorine gas. So there's the sodium metal, and you put it in a container with chlorine gas, and it reacts rather vigorously and forms salt, sodium chloride. There should be the general form written here, and there's not, so let's make it that way. So this is A plus B makes AB. In this example, we've got 2 sodium plus chlorine to give 2 NaCl. So you recognize a combination or a synthesis reaction because it has one product. The next category is a decomposition reaction, and this is sort of the opposite of the combination. This is where you have one reactant and it falls apart. So down here we have an equation for the decomposition of water. You could do this at home. Stick a 9-volt battery in a glass of water and see what happens. It'll make bubbles. Those bubbles are hydrogen gas coming off of one of the terminals and oxygen gas coming off the other terminal. The electricity causes the water to decompose into hydrogen gas and oxygen gas. And so the general form for this is AB, one reactant making more than one product. So you recognize combination because it has one product. Decomposition you recognize because it has one reactant and it's coming apart. Another type, which we haven't talked much about at all, is called displacement or single displacement. This is where one element displaces another in a compound. If you put metallic zinc in a solution of copper chloride, what you'll find is that the zinc metal becomes copper colored because the copper deposits onto the zinc metal. I always get confused between the two labs. Did you guys do copper nails, or was that my other class? It was the other class, okay. Otherwise, that would have been a great example. But since you didn't do it, I can't talk about that. Okay. What's happening here is that we've got zinc metal with copper 2 sulfate, and we're ending up with zinc sulfate and copper metal. The copper and the zinc are swapping places. So in our party analogy, zinc is a guy going to a party by himself. He didn't bring a date. And copper brought a date. Everybody mingles around, and zinc ends up leaving with copper's date. Okay? And then copper has to go home by himself. So one person got displaced. The general form here is that we have A plus BC going to AC plus B. So one of your reactants is an element, and one of your products is an element. And that element, those elements are switching places in the compound. There's a lot of stretching going on this morning, and I keep thinking people have questions. It's okay, go ahead and stretch. But then if you have a question, you might have to jump up and down or something. The other type, the last type we'll talk about, is a double displacement reaction. The combination reaction, the precipitation reactions, the acid-base reactions, and the gas evolution reactions all end up being a double replacement reaction. So the precipitation, gas evolution, and those acid-base reactions. The general pattern here is AB plus CD goes to AD plus BC. So here we have one couple going to the party and another couple going to the party. It's interesting, in previous semesters they were going to the prom. I don't know why it suddenly switched to a party, but it did. Anyway, they're going to the party and they end up switching partners and leaving with somebody else. That's a double displacement, sometimes called a double replacement, because you've replaced your date. So precipitation reactions do this, acid-base reactions do this, and many of the gas evolution reactions also do that. So here's the flow chart for this type of categorizing. General chemical reactions can be divided into these 4 categories: synthesis, decomposition, single displacement, or double displacement. Now, any reaction that's in one of these categories is also going to belong to one of the categories where we look at what's happening. So many things can be classified more than one way. So this is an example, actually 4 examples. And this is the sort of thing you should be able to do on an exam, okay, to show me that you understand classification of reactions. So we're supposed to look at each of these and decide, is it a synthesis, decomposition, single replacement, or double displacement reaction? So let's look at that first one. We have the element aluminum, and we have a compound, and we're getting aluminum in a compound and a different element, hydrogen. So what kind of a reaction is that? That's a single displacement. So aluminum went to the party by himself and ended up leaving with hydrogen state. Makes you wonder about the morals of these elements. Okay, any questions about that one? Letter B, what's going on with that one? Here we have one compound and a different compound, and then we end up with 2 other compounds. This is a double displacement. Here copper is with sulfate, and now copper is with hydroxide. Potassium came with hydroxide, but he's leaving with sulfate. So both have switched partners. This is a double displacement. If we were looking at the other form of classifying by what happens, what sort of a reaction is this? We had oxidation reduction, we had gas evolution, we had precipitation, we had combustion, and I think there was one other I'm blanking on. This is a precipitation reaction, acid-base, that's the other one. This is a precipitation reaction. We have two ionic compounds that are aqueous. When we mix them together, a precipitate forms, okay? So you should also be able to recognize that as a precipitation reaction. How about letter C? Here we have one element plus another element gives us one compound as our product. Synthesis. Those are generally really easy to recognize. In that other type of classification, what sort of a reaction is this? What happens when we have a metal reacting with a nonmetal? It's an oxidation reduction reaction. So remember, oxidation reduction reactions were things reacting with oxygen, metals reacting with nonmetals, and often nonmetals reacting with other nonmetals. We can see, oh nice. Now we can't see anything. But you can always go back and look at that. Let's look at this guy and see what's going on. Potassium, the element, does it have a charge? No. Okay, an element can't have a charge. Only ions in a compound can have a charge. Nature doesn't like charges to be separated. Okay, you can't have a bowl of potassium ions without having chloride ions or some other negative ion to balance the charge. You just can't keep them separated like that. So any element has a charge of 0. So here potassium has a charge of 0. I know we don't usually write it like that. And bromine is an element, and so it has a charge of 0. In this compound, we have a metal and a nonmetal. This is an ionic compound, right? It has 2 ions. What's the charge on the potassium ion? It's in group 1, it's +1. What's the charge on the bromide ion? It's -1. You look at the periodic table and the noble gases are 0 and you count backwards. Bromine is 1 column over. It's got a -1 charge. How did potassium go from having no charge to having a +1 charge? Something happened with the electrons, right? Did it gain an electron or lose an electron? It lost an electron. So is that oxidation or reduction? Oxidation. Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. If one got oxidized, the other got reduced. Bromine went from 0 to -1 by gaining. Reduction is gaining electrons. So this is also an oxidation reduction reaction. Okay? What am I doing? Bottom one. We've got copper 2 chloride reacting to form copper and chlorine. What kind of a reaction is that? Decomposition. We don't really have, well, I wouldn't expect you to recognize that as an oxidation reduction reaction, although it is. But you're not really equipped to classify that in the other manner. But decomposition, we recognize it easily because it has one reactant. So it's decomposing. Any questions? This is the chapter in review. So my students are always asking me for study guides. This is the study guide right there. Okay, just brief summary of the chapter, the things we talked about. These are the chemical skills. This is what you should be able to do. You should be able to determine whether a compound is soluble. I'll give you the solubility rules. You should be able to write equations Apparently you should be able to write equations for acid-base reactions twice. What? Goofy people. I didn't write this slide. Okay. You only need to be able to do it, you know. That's not twice as important. Anyway, these are the things, the skills that you should have, okay? And then on Mastering Chemistry, I will be posting study questions that will be multiple choice questions similar to what might be on the exam. Here's just a couple examples for us to practice predicting products and balancing equations, because I think many of you could still use some help with that. So predict the products and write a balanced molecular equation for this reaction between copper 2 nitrate and ammonium sulfide. So what do? You go, I don't know what to do. No, we look at it and we think, well, those are two ionic compounds. They're aqueous. When I dissolve an ionic compound like table salt in water, it breaks apart into the individual ions. So let's start out by writing the individual ions. Okay, so looking at this formula and dividing it into ions is something we learned how to do in Chapter 5. And I think some of you are still kind of iffy on that. Okay, this isn't going to go away. Okay, we're not just going to forget about that. It's going to keep showing up. You got to figure it out. Nitrate ion has a -1 charge. That's something you have to memorize. You just have to. From the charge on nitrate, we figure out what the charge on copper is. Because copper is not in group 1A, 2A, or 3A, or zinc or silver. Those are the ones that always form the same charge. Copper is one that can form 2 or more charges. And so the only way we can tell what its charge is in this compound is to look at the other ion. There's 2 nitrate ions. Between the 2 nitrate ions, we have a total of 2 negative charge. We have 1 copper ion. We need a total of +2 charge. So the charge on this copper ion must be +2. In order to predict the products correctly, you have to know the charges on the ions. You just do. Okay, ammonium and sulfide. Ammonium is another one of those polyatomic ions that you have to memorize. It's NH4+. Sulfur is a monatomic anion. Sulfur is predictable from the periodic table. It's 2 columns over from the noble gases. It has a -2 charge. You start at argon and you go -1 to chlorine, -2 to sulfur. So if you had forgotten the charge on ammonium, you could figure it out from the charge on the sulfide. The sulfide has a -2 charge and there's only one of them. And so if there's a -2, there must be +2 over here. And we see that there's 2 of those ammonium ions, so each of the ammoniums must be +1. So sometimes you can figure it out. And sometimes you could look at other parts on the exam and figure it out and use that information on the question that's giving you trouble. So what we're going to do here is we're going to have these swap partners. This is going to be a double replacement reaction. Okay, so copper and sulfur are going to be together, and nitrate and ammonium. The order in which you write these does not matter. Cu2+ and S2-. And then we have NH4+ and NO3-. This is not an acid-base reaction. In an acid-base reaction, one of these pairs would be H+ and OH-. So in order for this to actually be a reaction, one of these things has to be insoluble. So to save yourself a little work, potentially, I would recommend going and checking the solubility of these compounds first. If you look up ammonium in the rules for solubility, ammonium compounds are always soluble, and nitrate compounds are always soluble. This one's going to be soluble. So I'm just going to make a note to myself. That one's aqueous. Look up copper and sulfide. Copper doesn't show up in the list. Sulfide does. It says that sulfides are generally insoluble, if I remember correctly. And then there's some exceptions. Copper is not one of the exceptions. So this is going to be a solid. So that tells us there is a chemical reaction and we have to finish this. We look at the copper 2+ and sulfur 2-. Their charges are opposite but equal. So we just push them together. +2 - 2, they add up to 0 all by themselves very nicely. So CuS is the formula for that, and then we put S in parentheses afterwards to indicate that that's an insoluble compound. That's our precipitate. Then the other one, we've got ammonium with a +1 and nitrate with -1, and so those are also going to be just one of each pushed together. This came up in the nomenclature worksheet. I think it's called Study Guide 2 that we did. Why don't we write this with the two nitrogens together? Why don't we write it N2H4O3? Because it's two ions. They're two polyatomic ions. And when we write it this way, NH4 and NO3, it's just much clearer to everyone what belongs with what. Okay? So just, don't worry about rearranging and combining or anything. Just write the cation first and then the anion. And that, I ran out of room, of course. That's aqueous. And then we have to look at the equation and balance it. So on the left, there's 1 copper. On the right of the arrow, there's 1 copper, so that's okay. On the left, there are 2 nitrate ions. And on the right, there's only 1. I can fix that by putting a 2 in here. That multiplies ammonium nitrate by 2. Now I have 2 ammoniums and 2 nitrates. Then I go to this next one. I see I have 2 ammoniums there. And you think, well, that's convenient. I just made this to be 2 ammoniums. So that's good. Here I've got 1 sulfur, and there's 1 sulfur over here. These double displacement reactions generally balance themselves fairly easily if you have the correct formulas. If you don't have the correct formulas, it may be impossible to balance. So there's the equation. Any questions? Here's another one. Predict the products and write a balanced molecular equation. Silver nitrate, sodium chloride. 2 ionic compounds. They're not an acid and a base. And so we're going to swap partners. We have to write the individual partners, the individual ions underneath. So we've got Ag and NO3. Hopefully we remember, since we just did one with NO3, that that's a minus. Silver is one of those exception elements. Group 1A, Group 2A, Group 3A, and then zinc and silver. Aluminum is in Group 3A. It's a 3+ charge. If you go down one step, zinc is 2+. Go down another step, and silver is 1+.